I drew out Lee Hart's Batt-Bridge diagram, and then the formulas example. But just to point out, squiggly thing here is a resistor. Those are both power resistors. These three things represent our LED bulbs. Also, LEDs stand for light emitting diodes. So these are all symbols for diodes also. They're diodes that emit light. So unlike regular bulbs where you can hook them up either way and they work, diodes are like one-way electronic valves, I guess you would call them. So each one has a plus and a minus. So all of these diodes, these points, mean something. So on our plus or positive line that goes to the positive pole of the battery pack, you would have the positive line of one of your red diodes and the positive line of your green diode. And then the other side of your green diode, you'd have the negative line of your green diode and the negative line of your red diode. Then going to your center tap, you'd have the negative off of your positive red LED, I guess you would call it, and the positive off your negative red LED, I guess you would call it, come together to your center tap. So all these LEDs have to be in the correct order for this to work properly. The light would be set up about like this. The positive of the green LED is on this side, and the positive of this LED is right here. The negative of the green LED is on, let's see here, where does it say the negative battery pack side? So you've got the negative of the green and the negative of the red goes together for the negative lead. The positive of the green and the positive of the red go together for the positive lead. And then you've got the negative of this red, positive of this red come together, and that's your center tap. And then to help hopefully explain it a bit more, I added our resistors in. So you got the negative of the green, the negative of the red going to this resistor, going to the negative of the battery pack. You've got the positive of the green and the positive of the red going through this resistor right here, going to the positive of the battery pack. And like I said, you've got the remaining negative, the remaining positive from these two, they go to the center tap. So all these LEDs have to be arranged the proper way, and then have to have the proper resistors attached to do its thing. And then to figure out what resistors you need, you start off with whatever your pack voltage is. That would be represented as X. You want half of your pack voltage because you're measuring each half. So it would be X divided by 2 equals Y. So we got Y divided by 0.15, because that's about what we want milliamps, right in the middle of between 10 and 20 milliamps, equals Z. And then Y times 0.015 equals, I guess this would be ZA and ZB. ZB. So then you figure out, that's how you can figure out what resistors you need. And then you want to double up the wattage represented by ZB, because you want enough watts to handle the whole pack, I guess you would say. And then you want your power resistors to be at 1% tolerance. So as an example, for the 24 volt battery balance monitor, we've got a 24 volt battery pack. Half the pack is 12 volts. 24 divided by 2. 12 divided by 0.015 equals 800 ohms. That gives you your ohms. And then 12 times 0.015 equals 0.18 watts. That gives you your watts. And then you double up your watts. That's almost 20, so 20 and 20 is 40. That's just under a half a watt. So you would need an 800 ohm, half watt, 1% power resistor for a 24 volt battery balance monitor.